Hello everyone, we are more or less at the fag end of this particular course. Initially we talked about wastewater, then water. Obviously we are yet to talk about residuals, but we will wrap that up after this particular session. So in this session and the couple of sessions preceding this session, we were looking at removal of specific compounds, let's say, right? Specific compounds like calcium, magnesium, and if there are trace compounds, with ion exchange or with respect to nanofiltration or by using reverse osmosis. That's what we have discussed. In this line of understanding, if I may say so, or learning, let us look at one more aspect here. So we are going to discuss aeration today, right? But we did come across this aeration earlier. Where did we come across this? That was not in the context of water treatment though, or drinking water treatment. It was in the context of wastewater treatment or sewage, let's say, right? It was in the context of sewage treatment or wastewater treatment. There we were looking at supplying oxygen, electron acceptor to the relevant microbes so that they can catalyze the reaction where the waste or our waste is oxidized by oxygen, right? That's where we looked at. So in the context of water treatment too, we do, or obviously we are going to come across or use aeration, but where are we going to use this? Typically this, if it is used, will be used before primary treatment, so during or at the fag end of preliminary treatment. Right? But the reason we are discussing it here now is I wanted to look at or look at the discussion or consider the discussion with respect to specific compounds in one go, let's say, right? So here we are talking about aeration and such. So let's look at what compounds is it that we typically try to remove by aeration. So obviously if there are any gases that I want to remove, that's something that I can look at by applying or employing aeration, right? Aeration. So here I am talking about change in gaseous phase or change in phase, pardon me. Hydrogen sulfide, again H2S, remarkably reducing compound or strong reducing agent. It's corrosive too, and also more importantly, even at very low concentration, it gives out considerable odor like a rotten egg smell. So depending on your source and such, you might have to remove your hydrogen sulfide. But rarely do we come across this in the context of water treatment, but that's something I wanted to point out. And if you have excess carbon dioxide or H2CO3 in your water, to save up on your dose of lime during softening, you can purge this carbon dioxide rather than adding lime, right? If you remember the lime soda water softening process, all the lime that we added initially was to neutralize the carbon dioxide that was in the dissolved phase, which is in equilibrium with H2CO3. Or one other way is to strip the water of carbon dioxide. So that's one particular way. We are going to pass air through it and the equilibrium is going to change and this carbon dioxide is going to leave the relevant system, let's say, right? So that's one aspect. But typically, at least in the context of water treatment, we are going to look at aeration in the context of or for iron and manganese removal. So let's first understand why we need to look at removal of iron and manganese and what are the typical states or forms these are present in and in what forms are they troublesome to us. Obviously, anything in excess is an issue, and we also already looked at the Bureau of Indian Standards which presents the information about the different standards for different compounds and such, right? So you can look at the standards there. So here we are looking at iron in the +2 oxidation state, ferrous, and manganese 2 in the +2 oxidation state. But in which conditions do they exist? They exist in reducing conditions, typically which goes hand in hand with acidic conditions, let's say. So reducing conditions meaning reducing environment, where is that going to be prevalent? That's going to be prevalent when your system has no access to the oxygen or to oxygen, which is one of the most widely available electron acceptor or the oxidizing agent out there. So where on earth will you have little oxygen? So obviously it's below the surface. So in the aquifer below subsurface, you will have relatively low oxygen content. So, that is one aspect to keep in mind. Typically iron, let us say deposits or Fe2 plus is present, and if you have an industry nearby, why I am saying this is we now have an industry nearby Roorkee, near Haridwar rather, and the villages surrounding this particular industrial zone, not one industry, pardon me, an industrial zone, are experiencing the adverse effects of very high ferrous iron, or ferrous, I guess, yes, iron, and they did not face this issue earlier. So, one aspect was I guess, rather than wastewater being discharged that is high in iron content, another aspect that was occurring was acidic water coming in contact, and then deposits which were immobile now being mobile Fe2 plus, and then they creating havoc with the digestive system of the relevant villages. And also once they take this Fe2 plus out, that is going to also oxidize to Fe3 plus. Fe3 plus is more insoluble than Fe2 plus, and that is going to create issues too. So, we will look at that later. So, that is one aspect to keep in mind, right. So, where are we here? I guess reducing environments, typically we see them in the subsurface, let us say, right. And one aspect to note is Fe2 plus and Mn2 plus are remarkably soluble. Why is that an issue or not an issue? If it is insoluble, they would have precipitated out in the subsurface. Because they are soluble, at least because these forms of Fe2 plus and Mn2 plus are soluble, they will flow with the groundwater, right. So, they will flow with the groundwater, and what else? Remain in water following conventional treatment, but precipitate at the point of use. So, one aspect is they will flow with the groundwater and can create issues or stains whenever you what do we say, use them in your bathroom or sink or such. You would have seen this yellowish, orangish stains, that is typically due to iron and or manganese, right. Another aspect is because they are soluble, right. Until now we have looked at primarily suspended solid removal in water treatment, followed by disinfection, let us say. Depending upon the dose, you will not remove Fe2 plus or Mn2 plus, but we will come back to that. In water, we were typically trying to remove suspended solids. So, because Fe2 plus and Mn2 plus are soluble, right, typically they will not be removed by conventional treatment, but once you use them or during your usage, and when they are exposed to oxygen for certain duration, they are going to precipitate out after transforming into Fe3 plus or Mn4 plus, if I am not wrong, and that will lead to stains on the plumbing fixtures and in laundry. That is something to keep in mind. And it also looks like it also supports, the precipitation supports the growth of iron bacteria or iron slimes in well screens and distribution systems. That is something to keep in mind. So, first we need to understand some background or have some background. Before I go to that, let us look at what we have. Typically, we are concerned with the reduced forms which can be oxidized due to the change in the environmental conditions. Reduced forms which are more mobile, right, more mobile, because they are soluble in water, are Fe2 plus and Mn2 plus. Reduced form oxidation state is relatively less. It is the one that has the electron, right. With the electron, that is why it is reduced or less oxidation state here. If it is oxidized, right, it has given away the electron to an electron acceptor, then the oxidation state will increase Fe3 plus. It is losing an electron, right, electron with the negative charge is being lost. So, you have oxidized form here and also oxidized here. But the issue here is that now these Fe3 plus and Mn4 plus, they are not soluble, but they will precipitate out in the form of FeOH thrice or MnO twice, O2, right. So, this is one background. So, here we are coming across some terms which I freely used in the context of, I guess, wastewater and sometime in the water treatment, but here let me look at some of the aspects here. Here we are talking about inorganics, right. Fe2 plus not an organic compound, but an inorganic compound. Inorganics, relevant chemistry, there are four major aspects to look at: acids and bases, right. In this context, the example was H2CO3 acid being in equilibrium with H plus, HCO3 minus, and so on, let us say, right. So, this is acid and base, and then we have aqueous complexes, as in Fe3 plus or even Fe2 plus. If it is at higher pH, it can form a complex with a ligand OH minus, electron rich, right. It can form complexes, right. And what else? We have precipitation and dissolution. the compound can be dissolved, or if it's in far excess of the stoichiometric ratios or such, the precipitation can occur. So, in that context, or where did we come across this? I guess we looked at lime softening and we were trying to remove calcium by precipitating it out as CO3 solid or magnesium hydroxide the solid. We came across this earlier, the principle of or the application of precipitation. So, another aspect I think we briefly touched upon in the wastewater aspect or wastewater relevant topic was redox, right? Redox as in transfer of electrons. You are going to have reduction and oxidation going hand in hand. In the context of wastewater, the reduced compound was our waste, right, CXHO, right, and the electron acceptor was oxygen, and then the final products, if everything goes according to plan, would have been carbon dioxide and water. You see relatively more oxidized form of carbon, let's say, right. Carbon is being oxidized and this was the reduced compound and this is the oxidizing agent, let's say, which is oxidizing your reduced compound. So, that is what you see out here. So, similarly here we are going to use these principles to understand how to remove Fe2 plus. So, key aspect is that Fe2 plus can be oxidized to Fe3 plus. In general, I guess I should have written it the other way, Fe3 plus plus electron. This is the standard way of writing, as in reduction is the standard way. For this, you will have the P naught values and such. You can think of it as your log K or such, or 1 by n log K, where n is the number of electrons. So, anyway, you have this, as you can see, where depending upon the transfer of electron, one form can go to the other. So, here Fe2 plus is in this phase initially, but once it comes in contact with an electron acceptor. What is the electron acceptor? Electron acceptor is the oxygen. Again, I am not balancing it out here, I guess, right. Let me not go into that aspect. So, oxygen can take the electron, right, which is being given by Fe2 plus, right, and thus this Fe2 plus can transform into Fe3 plus. Please note that for a redox reaction to go through, you have to have both the reduction and oxidation occurring. There can never be only oxidation without reduction. Why is that again? Because electrons, they won't float around in water. There can never be a pool of electrons, unlike the case of a pool of H plus and then pH being affected, right. So, if you want to have a redox reaction occurring, you need to have a reducing agent or reductant and oxidant, let us say. So, that is something to keep in mind. So, here Fe2 plus is the reductant, but it needs an electron acceptor for this reaction to go through. So, that happens when you have oxygen in contact. So, what happens to Fe3 plus that is formed? We know that Fe3 plus is remarkably insoluble, right, typically very insoluble. It is not soluble, it does not stay in water. So, or does not want to, let us say, stay in water even at relatively medium or such concentrations. So, it will precipitate out as this solid, right. So, you can use this particular principle to try to remove Fe3 plus. Similarly, we are going to look at or can look at Mn2 plus. So, keep in mind that we are looking at oxidation of Fe2 plus, redox, right, oxidation of Fe2 plus, and then we are looking at precipitation of the Fe3 plus that has been formed when we oxidized Fe2 plus. So, that is something to keep in mind. So, principles that we used were redox and precipitation and dissolution. So, let us move on and look at the relevant aspects. To oxidize iron and manganese, let us look at the overall reaction here. So, O2 plus, earlier we looked at 1/2 reaction, I guess, right, Fe2 plus going to Fe3 plus plus electron, let us see, right, and what is the, who is going to accept this electron? Oxygen is going to accept the electron, oxidizing agent, electron acceptor. So, that is what you have in the presence of oxygen. Fe2 plus can again in relatively acidic conditions be oxidized to Fe3 plus, and similarly O2 Mn2 plus, right, it can go to Mn4 plus or be oxidized to Mn4 plus. One aspect here is, especially for this reaction, if the pH is low, right, this is particularly or low or even neutral, at least for this particular reaction, it is pretty slow, this particular reaction anyway. That's something to keep in mind, but we will come back to that, right. So, now that we have Fe3 plus and Mn4 plus formed, these are from here Fe3 plus and Mn4 plus, which are oxidized after oxygen oxidizes which are formed after oxygen oxidizes Fe2 plus and Mn2 plus. So, as you can see Fe3 plus, it is acting as a Lewis acid here. So, Fe3 plus, it will precipitate out as FeOH thrice solid or MnO twice the solid, and thereby again releasing H plus, I guess, right. So, that is something to keep in mind. So, the previous step which we looked at, where we are looking at oxidation, that is relatively slow and it specifically dependent on pH, and the precipitation though surprisingly is typically fast enough, right. In general, redox reactions are typically either pretty fast or they never reach equilibrium, depends on the relevant environment and such. So, redox reactions, that is always the case, right, as in kinetics plays a great or considerable role. So, let us move on here without digressing further. So, this is the aspect, but we need to look at some background. For example, let me write one more aspect here. For acids and bases, you can come up with an equation. For example, if it is HA, right, acid dissociating to H plus plus A minus, and you know that the equilibrium constant is Ka, let us say, pH equal to pKa minus log HA by A minus. This will be the concentration which we are approximating, using to approximate activity, right. pH equal to pKa minus log HA by A minus. It is just taking the logarithm and playing around with the values, and you will get it, right. We know that Ka equilibrium constant is H plus into A minus by HA, right. I am just giving the basics here so that people who are interested in learning can look at it in detail so that they can apply it later, right. So, this is the aspect, and from here we came up with one graph, right, and this point where both the protonated form HA is the protonated form with proton and A minus is the deprotonated form without proton, where the pH at which their concentrations are equal is going to be the pK, and on this we have pH and on this we have the concentration. Similarly, let us say for Fe3 plus electron going to Fe2 plus, right, you can come up with a relevant equation that will look something like the Pe is going to be equal to Pe naught minus 1 by n. 1 by n is equal to number of electrons being transferred, here it is 1, log Q dash, right, Q dash is the one without the electron. So, log of Fe2 plus concentration by Fe3 plus, right. So, you can come up with this particular equation for this half reaction. So, similarly, I can draw this particular graph here. So, here I have Pe, which will give me an idea about whether it is reducing conditions or oxidizing conditions, right. So, I have Pe out here and relevant concentrations, let us say out here, let us say. So, again I will have a profile something like this, and the point at which both are equal obviously should be equal to Pe naught. Pe naught again can be looked at, or you can transform that to Eh naught. We will look at that later, but keep that in mind. That is one aspect to keep in mind, right. P naught. Here you will have the reduced form, the one with the electron. For example, here it is the one with H plus. So, here it is the one with electron here, and the one without electron will be out here, without electron, and here it is without H plus or the proton. So, why did I draw this particular graph first? Because as you can see, we looked at this graph earlier multiple times, and the graph we are looking at now is similar to the graph on the right. So, again enough of that, but what does it tell you when the Pe is less, right? When the Pe is less, Pe is equal to minus log activity of the electron. When will the Pe be less? Pe will be less when the electron concentration is high. This is the hypothetical value obviously when we say activity of this electron. So, anyway, when Pe is less, that means reducing conditions prevail. When reducing conditions prevail, what form is predominating? Fe2 plus is predominating. And when oxidizing conditions prevail, as in when you have high Pe, oxidizing conditions prevail. This is reducing conditions,
here oxidizing conditions. What form is prevailing? You can see Fe3 plus is prevailing. So, this also gives you an idea about what do we say, which form predominates when water has certain characteristics. With a simple ORP probe, you can put it in water and see whether it is what do we say, whether it typically is in reducing conditions or oxidizing conditions. So, let us look at that particular piece of information. So, EH, as I mentioned, you can look at it in terms of PE, right, PE of the particular sample, and you have pH here on the x axis, let us say. So, this is like a predominance area diagram, something that we looked at earlier. So, forms of iron in water as function of redox potentials, right, redox potentials versus pH constructed with what is the total iron activity is 10 power minus 7, and this total iron can be in the form of Fe2 plus or Fe3 plus, which can also be precipitated out, right, that is something to keep in mind. And it also has some sulfate and other carbonate species, let us see, temperature and pressure are given, but let us not go into that. So, when the EH is high, water is oxidized, when our oxidizing conditions prevail, when PE or EH is less, reducing conditions prevail, that is something to keep in mind. When reducing conditions prevail and pH is relatively less, you see Fe2 plus predominates, right. But in relatively oxidizing conditions, what do you see? You see that Fe3 plus prevails, right, Fe3 plus, right, Fe3 plus prevails. Here you see the complexes, aqueous complexes, which we discussed earlier. But at slightly higher pH or neutral pH, you see that FeOH thrice starts predominating. So, here it is this zone that I am talking about. So, in the neutral pH, this is the neutral pH in this range more or less pH 7 or 6 to 8, and in this relatively oxidizing conditions, what do you see? Fe2 plus will not stay as Fe2 plus, it will be oxidized, and that oxidized Fe3 plus will precipitate out. So, that is what you see here, right. So, we are going to use this particular background to look at the pH that you want to maintain and such. Same case with Mn2 plus, here Mn total manganese total is 10 power minus 6. At low pH and relatively reducing conditions, I guess it stays as Mn2 plus, but at relatively higher pH, here note that it does not occur, or the oxidation does not occur at neutral pH values, that is something to keep in mind. It is at relatively high pH values, typically we are looking at least pH of 9 and such. So, at pH of 9, you see that the solid is going to be formed, right. Even though if you want to have it at neutral pH, you can do that, but then the EH or the redox potential has to be pretty high, that is something to keep in mind, right. So, you can understand how it transforms, or how the system transforms between one form to the other based on the EH and the pH, based on the redox potential and the pH. In groundwater, where there is no oxygen, typically reducing conditions prevail, that is why Fe2 plus and Mn2 plus are what do we say, abundant. But out here above the surface, where oxygen, which is an oxidizing agent, is aplenty, you are going to have oxidizing conditions prevailing, and thus you see that the oxidized forms are going to prevail, and in general at neutral pH and such, if oxidizing conditions prevail, you see Fe2 plus and Mn2 plus, they precipitate out as FeOH thrice or MnO twice. So, that is something to keep in mind. So, let us go through. Iron and manganese can be removed in situ. In situ is in place itself. So, injection wells around the water supply wells. For example, if this is my water supply well that is drawing water out, I can have injection, let us say, of oxidizing agents or such that I am going to inject oxidizing agents or such around my particular extraction well. This is my extraction well, so that I can precipitate out Fe2 plus and Mn2 plus. So, it can be as simple as purging it with oxygen or a benign oxidizing agent, let us see, right. So, that is something to keep in mind. Sequestration, as mentioned, you know that, or we talked about aqueous complexes being one other way to what do we say, in one other form into which the inorganics, especially the metals, can transform. For that you need a ligand that we looked at was OH minus, but here if you add phosphate, right, that will make the relevant Fe2 plus and Mn2 plus remarkably more soluble, and they typically won't precipitate. So, here they are using the term sequestration, right. So, that is one particular aspect. So, treatment with green sand, right. Natural iron, it is, I guess, what do we say, not exactly right to call this an ion exchanger, but let's see the relevant reaction. Right, you are going to have green sand and they are going to coat it with this MnO2, right, different ways to coat it. And when that comes in contact with Fe2 plus at relatively higher residence times, you can see the relevant, I guess this is going to be reduced, but you see that Fe3 plus, Mn3 plus and Mn4 plus are going to be formed, which are the oxidized forms, which are then going to precipitate out, right. That is one particular way. So, this is the media which is coated with MnO2. But after some time, obviously all that media will have to be regenerated because it has been exhausted, right. This MnO2 is being reduced, let us see, I guess, right. Okay. So, I am going to add a strong oxidizing agent to oxidize this reduced compound or reduced form of manganese. Mn2O3 plus KMnO4 goes to this particular form. Again, I am what do we say, oxidizing it so that it can be reused. The media can be reused here, right. What is the media? The media is green sand. Okay, oxidation. So, we know that we can form precipitates. The title of this session was aeration. So, in general, as we saw, even at relatively moderate redox potentials, or relatively higher, but I mean not very high, but high enough oxidizing potentials or redox potentials, and at neutral pH you can easily remove Fe in the form of FeOH thrice. But Mn not really, you have to see to it that the pH is higher if you want relatively faster kinetics, right. So, that is something to keep in mind. So, what is it that can happen? So, I guess this is the overall reaction out here. This is added, I guess, or is relevant. If not, the pH is going to decrease, right. So, that is one aspect to keep in mind. Fe2 plus reduced form, oxygen, oxidant, reducing agent, oxidizing agent, and then you have the relevant precipitate out here, let us see, right. And then once it is precipitated out, you can let it settle and filter it out, right. Again, as I mentioned, aeration, typically we will use that in the preliminary treatment or right before primary treatment, or you can add chemical oxidizing agents. So, chlorine, different forms of chlorine, KMnO4, but this is typically costly, and with respect to Mn2 plus, or if you have Fe2 plus bound to natural organic matter, it is very difficult to remove it. We looked at aqueous complexes, right. Complexes, we need metal and ligand. Ligand examples, what did we look at? We looked at OH minus, we looked at phosphates. And another ligand, electron rich is NOM, which is a nuisance. And as you can see, it also acts as a ligand and complexes with Fe2 plus, right. Fe2 plus and NOM, right, at least with Fe3 plus it does form it. So, you see that if you are adding an oxidizing agent, let us say, you might not be able to oxidize the Fe2 plus because it has formed a complex with the natural organic matter. So, that is something to keep in mind when you are adding oxidizing agents, or even trying aeration when your NOM is very high, if it is bound with the relevant metal. That is something to keep in mind. Again, KMnO4, relatively strong oxidizing agent, but relatively costlier too, right. So, the relevant reactions. So, here we will look at stoichiometry or such. These are the kinds of questions that are typically asked. So, that is for you to look at. Again, HCO3 minus, typically to see to it that the pH does not decrease. Without it, obviously the pH is going to decrease, let us say, right. So, here you have the relevant solids being formed and Fe2 plus being oxidized, Mn2 plus being oxidized and precipitated out. And lime soda ash softening, Fe and Mn can also be removed during softening if pH is raised above 9.8. If you look at that EH-pH diagram, you will be able to visualize that, right. So, I guess some of it can be removed during lime soda softening too. I guess with that we are done with aeration, and then we will move on to looking at what do we say, residuals and their relevant treatment, right. With that, I will end today's session. Thank you.